Hello everyone, welcome back. In the last couple of classes we discussed about the turbulence models, the k omega turbulence model, k epsilon turbulence model and the blending of these two models, which is the SST k omega model. And we saw that these models work well in for certain problems. Okay, SST k omega particularly is very useful if your flow has got separation. And again all of these models also have many different versions, okay, which were basically proposed at different points of time. So, when you are using it, you have to make sure that which version you are using, and you should also read the relevant paper to basically find out what kind of coefficient that you require to simulate a particular flow. Okay. So, I mean it is very important to know about your flow. If you are expecting your flow, I mean that it will have separation or a shock or expansion, accordingly you have to basically use a model which is best for those kind of flows. Also you have to make sure that your coefficients, the model coefficient that you are using are correct. Sometimes you have to tune the model coefficient also, okay, like I talked about this structure parameter or the basically viscosity limiter, that you may have to change in certain flows to get a better behavior compared to the experiment, right. So, that is why I always insist that when you start with the turbulence modeling, okay, you have to make sure that the model that you are going to use is validated for the class of flow that you want to simulate. Okay, let us say you want to simulate a flow which is having separation, you should not be using, for example, a model like k epsilon model. Now, you can validate the k epsilon model for a attached flow and then continue to use that model for a separated flow. That is not going to give you correct result. A very common example is let us say you want to predict the lift on a wing at a different angles of attack, right. So, your CL versus alpha curve, if you see, it will go something like this, okay, and at certain point your this will be the point of CL max, okay, and after that it will start dropping, right. So, this is the stall, okay, this is the stall angle, okay. So, for example, if you want to use the k epsilon model, so what will you see typically, and I think I have seen this kind of diagram earlier, that it's going to work very well, and then there will be abrupt stall maybe early or maybe late, and your CL max is also not predicted, right. Why? Because as you increase the angle of attack, so this is your alpha and this is your CL, okay. So, as you increase the angle of attack, the flow is going to be separated. So, you had this initial flow, let us say this is the wing or an aerofoil, the flow is attached, nice, any model will give you the good result, okay. But as soon as you go to a very high angle of attack like this, okay, or maybe let us make the same aerofoil, okay. So, as soon as you went like this, okay, your flow is going to be separated here, okay. Now, where is the onset of separation, okay. So, that will basically dictate what is the lift coefficient that you want to get, how big is the separation, okay, whether it is closed separation or open separation, okay. So, all these questions that you need to basically discuss or understand, and then only you will be able to use use CFD very effectively, okay. So, knowing about flow is very important, okay. As you go to high angle of attack, you know that flow is going to separate, okay. So, you should be very alert, very careful, okay, let me change the model and look find the model which can make the predictions better. Then also it may not be very successful, okay. Sometimes the flow become inherently unsteady, okay. So, I mean there are some scales which are unsteady in nature. So, that time if you are using RANS, and no matter what model you are using, it is not going to give you correct result, because the RANS is the average steady state flow, okay. So, in that case either you have to switch to URANS, which is very expensive. So, URANS, as we had discussed, is unsteady RANS, okay, or you have to do more expensive approaches like LES if possible, or in between a RANS and LES, which is the detached dissimulation, okay. Now, we are going to look at a very interesting model, which is called the transitional model, okay. So, the flow may be in some region it may be laminar, in some region it may be turbulent, and in between it may be transitional, right. So, you know that when the flow is laminar, the skin friction is low, okay. As soon as you go to turbulent, the flow skin friction is becomes very high, right. In the transitional region it starts rising, okay, and the transitional region is very high, and then the turbulent region is basically higher than the laminar flow, right. So, if you are using a model, a turbulent model in a laminar flow, for example, or certain region where it is laminar, okay, it is going to produce the viscosity, eddy viscosity, which is not there in the flow. It is giving you an artificial mixing which is not physical, right. So, it is not going to give you the correct behavior. So, with that basically philosophy that we need to predict the behavior where the flow is changing from laminar to turbulent, the transitions model have been developed. There are 2-3 transition models in the literature. I am going to discuss one, but there are other models also. For example, one model is basically 4 equation SST K omega model. Okay, that is the one model. It is also called transitional SST model. Okay, the other name is transitional SST model or the SST K omega model. Okay, so you should be very careful about the nomenclature. Okay, K omega is standard K omega, SST K omega is a blending of K epsilon and K omega. Transitional SST model is basically SST model, but some changes in the K omega equations. Along with that, you have 2 more equations. Okay, and I will discuss, I mean, come to those 2 equations very soon. Then you have basically K, KL and KT equation. Okay, it is also called the laminar kinetic energy model. Okay. Okay, so here you can see that there is another term. So, there is a turbulence kinetic energy KT, okay, but there is another term which is KL. Okay. So, I think this is not K, this is KL and KT, okay, and then there is another term. Okay. So, this is a laminar kinetic model. So, you not only solve for the turbulence kinetic energy, but also solve for laminar kinetic energy. Okay. And then there are some other I mean transition models which are coming, because as we become more and more ambitious. So, initially when the CFD was started, okay, it was like just the laminar flow we wanted to study, then we went to fully turbulent flow and we found some success with the different turbulence models. Okay, now we have become more ambitious and we want to do transitional flow also, and we want to basically capture full regime. The flow can be laminar in one region, turbulent in one region. Okay, so, if you want to just see this boundary layer where the flow is laminar or turbulent, I also discussed in the last class. Okay, so, okay, before that I think this is KL, KT and omega. So, you had K omega, but now you have the scale which is the laminar and turbulent kinetic energy, they are separated. The laminar kinetic energy will be lower than the turbulence kinetic energy. Okay, so, if you want to do this maybe on a boundary layer. Okay. So, this is the laminar, flow is initially laminar, this is the edge of the boundary layer, then it become transitional little bit, okay, and then it become, I mean, fully turbulent. Okay. So, you have region, this is, I will call this laminar, okay, this is transitional and this is turbulent. Okay. The range works here, or the most of the turbulence model, fully turbulent flow model works here. The laminar you do not require eddy viscosity, so mu t equal to 0, okay, and in between you can have, so this will have mu t, and this is a value, let us call it mu transitional, which is basically in between mu and 0 and mu t, right. So, can we have a model which predicts all the regions? Okay. So, one approach is look at a term which is called intermittency. Okay. So, what is intermittency? It basically defines how much the flow is intermittent. Okay. So, if you look at the laminar flow, I mean it is a very nice smooth flow, okay, and basically particles are not jumping here and there. Okay. So, it is not intermittent. Okay. You can predict the behavior here. So, in this case you will say intermittency is equal to 0. So, this is gamma equal to 0 here. Okay. On the other hand, the other side of the spectrum, you have the turbulent flow, where there is a very high intermittency, you have eddies of all sizes, okay, particle jumping from one layer to another layer and so on and so forth. So, here we will call it gamma is equal to 1. right. In between you can have transitional region, where if you look at the theory of turbulence, you will see that first there will be 2D instability, then there will be 3D instability from the laminar flow, and then you will have the formation of these small islands which are kind of looks like eddies, okay, and then they become more and more violent, and finally flow becomes turbulent. Okay. So, here the intermittency can be between 0 to 1. Okay. So, intermittency you can think of it as an indicator whether the flow is laminar or the turbulent. So, we will be using this intermittency in our equation K and omega equation, for example. So, we will be discussing this 4 equation SSTK omega model, okay, to basically find out where there will be production of kinetic energy and how much the production will be. So, if the flow is not turbulent, there is no production of the kinetic energy, turbulence kinetic energy, right, and how much the dissipation will be, and so on and so forth. Okay. But then there is another question, how do you find like in the flow where this gamma should be 0 or where the gamma should be 1, or where basically it will be between 0 to 1, right. So, that is another problem that we have. That means that how do you find out the onset of the transition, right. So, this point is called the onset. So, you can call this as onset. Okay. This is where it onset started, and this is basically the your length of the transitional region. This is the length. So, where it is starting and where it is ending. Okay. So, the onset of a transition and end of the transition. So, that is also I mean something that needs to be predicted by the model, right. Yeah, in fact, in the earlier models, even if you are using a transitional model, you had to give, okay, this is the onset, this is the point I want the flow to become transitional, and then it automatically start changing the value of mu t from that region, otherwise the mu t will be 0. But now models are smart, they can predict the onset of transition, and also they can predict basically how much will the size of the transition, when it will become turbulent, whether it will become turbulent, and those kind of things. Further, the transition can be of many type. Okay. There can be natural transition, that means you do not put up the flow anywhere, the flow will naturally become transitional. Okay. Starts with laminar flow and it will slowly become transitional. Okay. Then you can have a transition where basically you are trying to put some perturbations. Okay. Maybe the free stream intensity is high, there is a turbulence in the background. Okay, and because that your transition will not be natural, but it will be kind of accelerated. Okay, it may so accelerated, that it may go to a stage which is called the bypass transition. That means this entire region that you are saying, it may be very small or may not exist. Okay, I mean may not exist to your eye, that it become transitional, it become turbulent in a very small region. So, that is called the bypass transition. You can also have a transition which is a separation induced transition, right. So, for example, I was talking about the example of this flow separation on an aerofoil or a wing, right. So, let us say flow is coming from this side, and then when it goes here, it becomes separated here, right. So, when it becomes separated, your flow may become transitional within the separation. Okay. So, this is called a separation induced transition. Okay. The flow may be laminar upstream, okay, but because of the separation, some activity started happening in the boundary layer, and that made the flow transitional. Okay. So, then again the prediction of the separation bubble is a task, right. What kind of bubble it should be, it is a open bubble or closed bubble. Okay. Flow may be transitional before it is, okay, then you have to find out how this bubble is changing the behavior of the boundary layer there, or flow may be laminar upstream. So, then it is a case of laminar separation bubble. So, all those questions come into picture, and that is why it becomes a very tricky business for the model to predict this kind of flows. So, the two transition models like KKL omega or KLK omega, whatever you want to say, or this 4 equation SSTK omega, they have certain merits and demerits in the sense that they can predict some of these transitions. Maybe one model can predict the natural transition well, but not the bypass transition. The other model can predict the separation induced transition better. So, you have to basically look at the behavior of this model. As I have been telling, The RAS model is, there is a lot of experience needed to use these models in a difficult flows, in a complex flow. Okay. I mean, for simple flow like flow in a pipe or flow in a channel, it is very easy to use, but when you have all this kind of complexity comes in and they are in your engineering flows. Okay, you want to use this turbulence model for engineering flows. Okay, so there you have to be very careful and you need to do a good study before you start using this model. Okay, so let us look at this 4 equation k omega st model. So the baseline equations are basically still your k omega, k and epsilon equations. So this is your k equation, okay, and this is your omega equation, but you see that there are certain changes in the equations. Okay. So this is your production of kinetic energy. So earlier it was Pk, now you have made it Pk tilde, okay, and then this is epsilon term which is the dissipation rate, and this term also has been modified, and finally you have a blending term which was F1, that one also has been have been modified slightly here. Okay. So other terms remain the same, but there are certain terms which have been modified. Okay. So let us look at the modifications of these terms. Okay. So the Pk hat is nothing but Pk multiplied by something called gamma effective. Okay. Or in other words, you can also take it as gamma. Okay. So gamma effective is basically, gamma is the intermittency as we discussed, and then this intermittency, I mean you can see if the flow is becoming transitional naturally, then of course you can look at the picture of this boundary layer and see how the gamma is changing, but if the flow is having separation, then you have to also consider the gamma due to the separation. So it basically takes the maximum of gamma and gamma due to the separation, the intermittency which is developing due to the separated boundary layer. Okay. So this what we are seeing here is that now my production of kinetic energy is no longer just basically dictated by your turbulence model, but there is a term which multiplies to this, okay, which basically controls the production of the turbulence kinetic energy. So let us say you have gamma effective equal to 1 equal to 0. Okay. So that is a laminar flow. Okay. So in this case your production of the kinetic energy completely stops. There is no production of the turbulence kinetic energy if there is no turbulence, right. On the other hand, if like gamma effective is equal to 1, this is a fully turbulent flow. Okay. So in this case it basically goes back to the original SST k omega model, right. Similarly, you can see here the epsilon also be changed. Okay. So here you can see that it takes a value, I mean forget about the gamma separation. Okay. Separation transition will not cover in the class, but you can go back and look at it here. You can write it here as minimum of so this is 0.1 or 1.0 on epsilon. So what it does basically, okay, no, this is incorrect, it cannot be minimum 0.11. So that has to be gamma somewhere. Okay. So what it says is that, okay, maybe it will be some function of gamma. Okay. So the dissipation is also controlled by gamma. Okay. So but what this modification says is that it if the flow is laminar, okay, when the gamma is equal to 0. Okay. So again I am saying that this is not gamma, but some combination of gamma which makes sure that it is 1 in the fully turbulent flow and a value greater than maybe 0.1 in other regions. Okay. So if the flow is laminar, the function works in such a way that you have gamma is equal to so the dissipation is equal to epsilon hat is equal to 0.1 into epsilon. Okay. See, yeah, I figured it out. So this should be, you can call it as minimum of maximum of gamma and 0.1 and then 1.0. Okay, multiply by epsilon. Okay, let us say the flow is laminar, then gamma is equal to 0, right, but you do not want to take 0, because whenever if there is no dissipation also, okay, then also you will have there is no turbulence also, then also you will have dissipation of the turbulence kinetic energy. That turbulence kinetic energy may come from the free stream, right, you have to dissipate that part also. So then also you will have epsilon hat will be equal to 0.1 of epsilon. Okay. This if in other cases it is by default 1.0, that means it recovers to the original k omega equation. Okay. And there is some modification in the f1 term also, as we saw here. Okay. So, because of these changes that now the pk and epsilon depends on the gamma. Okay, it may be possible that the idea that we had originally, that it should go back to the k omega equation near the wall, that may not work with the original blending function. So, that blending function is also modified to ensure that we have k omega very close to the wall, okay, even when the gamma is very small or gamma is equal to 0. Okay. So, let us look at the gamma equation. So, this is the gamma equation here. Okay. So, the 4 equations that we have. So, k equation, omega equation, gamma equation, which is the intermittency. Okay. And then you have R e theta equation or I theta t, you can call it, okay, which is the momentum thickness based Reynolds number. Okay. I suggest that you read about this momentum thickness I mean you can have if you have a bond area like this, you can define the thickness in many different ways. One is of course your bond area thickness with delta, where you say that your u is equal to 0.99 or 0.9 of u infinity, 0.95 of u infinity. Okay. Or you can have something called theta, which is given here, momentum thickness, okay, which is theta, or you can have a delta star, okay, which is basically your the displacement thickness. Okay. Without going into the details of this is a fluid mechanics thing, and I expect that you go and read it. Okay. So, the momentum thickness is used as an indicator to find out where the flow may become transitional. Okay. So, the purpose of momentum equation, because as I told you that omega can become 0 and 1 or in between 0 and 1, but it needs a location where it should be switched on. Okay. So, that location will be given using this momentum thickness based Reynolds number. Okay. And of course, you need some experimental data where you say that okay, if this is the momentum thickness, then the flow becomes basically transitional. Okay. So, you will be solving these equations, compare with the experimental data or computational data like came from DNS, and make sure that okay, if my R e theta t found from this equation is basically let us say R e theta critical, or then you basically turn on this gamma equal to 1 here, okay, gamma greater than 0 here, okay, and then you keep on calculating this R e theta t and keep on comparing with the experimental data till you basically see that okay, this value is in the region of the transitional flow or in the turbulent flow. Okay. So, this is used as an indicator. Okay. And this I mean the nature of these equations are again the same. You have the temporal term, okay, you have the term which is advective, then you have the production of this intermittency, production of the thickness, Reynolds thickness based Reynolds number, okay, and then basically this should be d gamma, okay, there is a dissipation of gamma, okay, and then we will have this transport, okay, which is there in both the terms. Okay, these equations are also heavily modeled, okay, and let me this is d here, okay. And you can see that the production of this gamma depends on 2 parameter. I mean there are many parameter, but there are many coefficients, okay, model coefficients, but there are 2 parameters which for which I want your attention is the f length and f onset. Okay. So, the f onset what it does is basically it switches the intermittency production. Okay. Before that there is no intermittency, okay, but it has to be determined by something. So, that is determined by this R e theta t equation. Okay. And f length basically controls the strength. So, if the production rate is very high, it may become turbulent early, right. So, going back to the same picture, when it becomes I mean when it becomes transitional, okay, and when it becomes fully turbulent, okay. So, this onset and length, this has to be determined, okay, and they are done by basically comparing your R theta t, which is also a transport equation. So, this R theta t is also being evaluated everywhere at every time, and is compared against the experimental data, for which you know that it is a robust parameter which has got distinct value in the laminar flow and in the turbulent flow and in the transitional flow. So, by keep on comparing this R theta t with those experimental data, we switch on this gamma, the gamma will work, then gamma will be used in your K and omega equation. So, in the K equation it will change your production, the dissipation of this turbulence kinetic energy, and omega equation it will change the blending rate as we saw earlier. Okay. So, this is what about the transitional model. Okay. Again you can see that many model coefficients there in this transitional model also. It is not within the scope of this course that I cover all the models, but let me just briefly give you some idea about this some of the other models, okay, which are used in the industry. So, right now we have been using this linear eddy viscosity model. Okay. So, basically your stress, Reynolds stress is proportional linearly to your velocity gradient. Okay. But in the literature you have non-linear eddy viscosity model also, which basically takes care of your anisotropy. Okay. What do you mean by anisotropy? That you have this u prime and v prime and w prime. Okay. So, what we do in this linear eddy viscosity model, we assume that they are of 1:1:1. Okay. In all the directions the fluctuations are basically kind of equal. Okay. That is an isotropy. Okay. But that is not true in the practical flow. Okay. And it can lead to some wrong predictions. So, what this non-linear eddy viscosity models does, I mean I have written only for the simple shear flow, is that it takes this Reynolds stress depending not only on the velocity gradient linearly, but also in a quadratic way or maybe a cubic way and so on and so forth, right. As you would I mean understand that this makes this model more expensive, but then these models work in certain flows. For example, this cubic K epsilon or these models like ERSM, ESM etc., they come in this class of non-linear eddy viscosity model. They are more expensive than the eddy viscosity model, but not much. Okay. Again here also coefficients can be tuned to produce the correct anisotropy. Okay. And it can basically produce better turbulent behavior in certain flows. But there is of course no theoretical foundation behind this. It is just that you are trying to make this model more and more complex if the flow becomes complex, that is how it is. Okay. But there is no underlying theoretical foundation that why it should depend quadratically or cubically, okay, or on higher powers. So, this one class of model which is non-linear eddy viscosity model. And finally, this model which is Reynolds stress transport is an expensive model. Okay. So, here we say, okay, so in the earlier slide is not u prime v prime, but you can call it u prime square, v prime square and w prime square. Okay. Basically the energy or the stress in all the direction, normal stresses. Okay. So, this Reynolds stress transport model, so it basically takes care of this anisotropy much better, because now we are not reducing all these normal stress component or the shear stress component into one single parameter, which is mu t, right. That is what we have been doing in the eddy viscosity model. But here we will be solving equations for u prime bar, u prime v prime bar, u prime w prime bar, okay, v prime bar, v prime w prime bar, okay, and then u prime v prime bar we have already done. So, there are 6 equations now. Okay, w prime bar. Okay. So, there are 3 normal stresses, okay, and then you have got 3 shear stresses. Okay. So, we will have 6 equations in your RSTM model, okay, Reynolds stress transport model, and you have to basically derive these equations the same way as we derive the turbulence kinetic energy equation, okay, separately for each of these. So, there will be 6 transport equations, and the nature of the equation will be very close to what we have been seeing. You will be a temporal term, you will have a term which represents the advection, there will be production term, there will be dissipation term, and there will be diffusion term. Okay. So, all these terms will be there in these equations also for each shear stresses, and there will be lot of model coefficients. And the one thing you will see that, let us say if you want to derive the equation for u prime bar, this is a double correlation, you will get a triple correlation as an unknown, right. So, it may be u prime v prime bar, okay, or maybe u prime v prime v prime bar, something like this. Okay. So, that you will figure out as you try to derive these equations for each of these traces. So, we wanted to close this equation, but the closure problem remains. Okay. Now, the closure problem has shifted to the triple correlation, that is what this model has done. Okay. But the idea is that as you go to higher and higher correlation, maybe the effect of modeling these terms may be lesser than the modeling it right here itself. Okay. Secondly, the anisotropy also, because you are doing this stress term separately. So, we are basically taking care of these terms separately, which is typically in the flow is like if the flow is in x direction, the u prime square will be 1.0, v prime square will be 0.4 and w prime square bar will be equal to 0.6. So, this is how the anisotropy is. So, this stress terms takes care of that. Okay, the production and adaptation term as you told that like the turbulence kinetic energy, if you want to derive those terms, you will get these terms accurately, but the diffusion terms are usually modeled, okay, as in the K-epsilon equation. It has got 6 equation, but this is less stable, and then the EVM equation, and the reason for that is that in the EVM equation we get an extra viscosity which is mu t. Okay. So, this mu t basically makes the scheme more stable, so because your effective viscosity is mu plus mu t. Okay, that advantage we do not have this in this particular equation. Okay, so this is less stable than the eddy viscosity model, but this has got in terms of like physical picture, it is looks more accurate, although there is modeling at the higher level. Okay, but it is definitely more expensive, and in practical situations it does not offer much advantage to like the most recent EVM based models like the K omega 60 and so on and so forth, but in some flows it may be a useful model. Okay. So, this is how the cost is. Okay. So, of course, the DNS is the most expensive approach. Okay. After that there is LES, and now these three that you see 1, 2, 3, these are basically your turbulence model, these are the RANS approaches. Okay. So, the most expensive here is the Reynolds stress transfer model, because you are solving 6 equations. Okay. And then you have the nonlinear eddy viscosity model, because your mu t is proportional not only to the del u by del t, okay, but also del u by del t square and so on and so forth. And the least expensive is basically mu t proportional to del u by del t, which is the linear eddy viscosity model. If you want to call it, this is a linear eddy viscosity model, which we have in this case. You have basically K epsilon, K omega, okay, SST, K omega, and also the transitional models. In this class, you have this cubic K epsilon, okay, and ERSM. Okay. This is RSTM model. It has also got some versions, but I am not covering those things. Okay. And then you have LES, which will be covering towards the end of this course. Okay. And DNS is anyway solving the Navier-Stokes equation as it is without any modeling, but the requirement of the grid size is very high, so high that it is not even affordable with the kind of computers or supercomputers that we have for a practical problem. Okay. So, this ends the discussion about this Reynolds average Navier-Stokes equations or RANS equations, turbulence modeling, and this I took some time to discuss about the RANS, because this is the model that we will be using the most. Okay. Unless you are in academia, the chances of using DNS is not very high. Okay. LES is now becoming a tool for industries for some problems, but still it is not mainstream. You will not be using LES for your regular design tool, or let us say you have want to do a parametric study, you will not be using LES. So, in most cases you will be using your RANS model, despite all the disadvantages that we talked about the limitations of these models. Okay. So, with that we will stop here. We will next discuss about the boundary conditions. Okay. I has basically delayed the discussion of boundary conditions because we also need to discuss about the boundary conditions for the turbulent parameters. Okay. So, that is why we will next take the boundary conditions, and we will also see how to set up the boundary condition for the turbulence parameters like K and like turbulence intensity or length scale and so on and so forth. Okay. So, we will meet in the next class. Thank you very much.